Okay, so the system shown below we're told consists of a homogeneous bar of mass m, which is pinned to ground at point O and moves in a horizontal plane. We're asked to let theta represent the angular orientation of the bar, measured in a counterclockwise positive sense. In this particular problem, we're asked to find the value of c, necessary for critical damping, assuming small oscillations, that is, when sine theta is approximately equal to theta. So in this problem, like we do in all vibrations problems, we're going to start by sketching a free body diagram of the system. And if I'll go ahead and sketch a two-side free body diagram here, just to be consistent with the previous chapter. And so in this regard, we know that the forces acting on the system, first of all, will be reactions at point O, which will be of magnitude OX and OY, respectively. And we know then we'll have a force due to the spring, which I'll call simply FSP for now, and a force to the dashpot, which I'll simply call FD. And they'll both oppose the motion, assuming that theta is measured counterclockwise positive as stated in the problem statement. And we can represent the kinematics in this problem by mass, in this case the inertia, I naught times the angular acceleration theta double dot. So in this case I need to spend a little bit of time figuring out FSP and FD. And so in that regard, let me sketch a little picture for you here. We can note that if this beam is allowed to deflect, or this bar is allowed to deflect an angle theta, that really what we're going to get here, assuming small angles, are forces which are proportional to the amount that the bar deflects at those positions. And so, for example, if I wanted to find this distance here where the spring force is applied, we know that that point is going to move, assuming small angles, an amount given by a theta. And that's kind of an arc length-like approximation. Likewise, if we want to account for how far the end's moving here, the arc length approximation is going to give me b times theta. What does this mean? Well, it means the following. If I go ahead and sum moments about point O and choose to do so in a counterclockwise positive sense about the end, I know this is going to equal I about O times theta double dot. And so what this means I'm going to get is minus FSP, the spring force, times its moment arm, which is A, minus FD times its moment arm, which is B, will equal I about O times theta double dot. Now I can go one step further here and note that the force in the spring is going to be the stiffness, K, times the amount that point of contact moves, which in this case is given by A theta, and I'll still have to multiply by the moment arm length, which is another A. If I use similar logic for the dissipative force, I'm going to have the dashpot constant, which is C, times the amount that end moves, and I should say the speed of that end, which would be B times theta dot, and I'll have to multiply by the moment arm length again, which is B. And so I'll get that is equal to I about O times theta double dot. And I can go one step further and say, well, I know I about O for a bar will equal I about the center of mass plus the mass times the distance between the center of mass and the end, which in this case would be quantity B over 2 squared times theta double dot. And if I go ahead here and note that I about G for a homogeneous bar is 1/12 ml squared, which in this case L is B, I can go ahead and substitute this all back in together and get the following equation of motion for the system under the small angle approximation, namely that I about O is going to become 1/3 times mb squared times theta double dot plus cb squared times theta dot plus ka squared times theta will equal 0. Now in this particular problem, I'm asked to find the value of C necessary to have critical damping, and so to find that, I'll start by mass normalizing this problem. That's going to give me, in this case, that theta double dot plus 3C divided by m times theta dot plus 3Ka squared over mb squared times theta is equal to 0. Now at this juncture I can find the natural frequency of the system because I know it has to be the square root of 3Ka squared divided by mb squared. And I also know that 2 times zeta times omega n has to equal 3C divided by m. In the case I'm looking for the critical damping constant, I know I can set zeta to be exactly 1, which means that 2 times omega n, that is the square root of 3Ka squared divided by mb squared, has to equal 3 times C critical divided by m, or that C critical has to equal 2m divided by 3 times the square root of 3Ka squared divided by mb squared. At this juncture, you can just go ahead and plug in the numerical values you're given for k, m, a, and b, if they are indeed given. If not, you can leave it symbolically here and just wrap up the problem. I'll leave that up to you to do, and wish you the best of luck. Take care.